Open your codebase. Run a global search for 768, or whatever number you use for the mobile cutoff. Watch what lights up. You'll likely find a media query in your CSS, a match media call in your JavaScript, an ARIA attribute in your markup, a uniform in a GPU shader, and a static string sitting in your AI context payload. 5 different languages, 5 different files, each one independently claiming to own the exact same adaptive decision. Take that AI context payload. The model is trying to reason about the interface based on a JSON data block that says the layout is wide and spacious. But on the user's actual screen, the window resized 10 seconds ago, and they're looking at a compact, narrow column. The model is blind to reality because its copy of the layout state is stale. The application didn't crash, no error logs fired. The systems are functioning exactly as written, but they are operating on scattered, decentralized truths. The interface is simply lonnying fluently in several dialects at once. It is tempting to blame the styling tools here, but modern CSS is highly capable. We have container queries that respond to specific component widths and fluid clamping that scales typography beautifully across viewports. The limitation is jurisdiction. CSS controls visual styling. It has zero authority to tell a WebGL shader how to render. It cannot update the accessibility tree for a screen reader, and it cannot talk to a language model. We are using a styling language to govern an adaptive decision that has outgrown visual boundaries. Container queries fixed where a layout asks the question. They did not fix how many distinct systems have to answer it. A breakpoint is a scattered conditional, a rigid number like 768 pixels, copied and pasted. A boundary, however, is a deliberate decision. It takes a continuous environmental signal, like viewport width, scroll position, or pointer type, and quantizes it into a discrete named state. Because the physical world is continuous, signals are noisy. Standard breakpoints rapidly flip the UI. A boundary adds hysteresis, a dead zone around the threshold. Inside this band, the state holds its ground, absorbing noise. It transitions only upon cleanly exiting the zone. The interface gains memory. You stop writing disconnected conditionals and start projecting stable state machines. Those 5 scattered files are stripped of their isolated authority. The adaptive decision is moved into a single canonical location, a document graph. This graph is content addressed. Every time you define a boundary, the system generates a cryptographic hash derived from the exact byte stream. If you change a threshold by 1 pixel, the hash changes. The graph operates as an immutable kitchen ticket. Once the adaptive intent is sealed into that hash, no downstream system can rewrite the order. The central node is the only source of truth. With the truth secured, it has to reach the application. This is the forward path, known as cast. Cast is a projection discipline. The single graph lowers its verified state into every environment your app runs. It emits a CSS variable for layout, an ARIA attribute for screen readers, a shader uniform for the GPU, a TypeScript union for logic, and an updated manifest for AI. Because all 5 systems are reading their state from the exact same cryptographic hash, they cannot disagree. In this architecture, silent drift is mathematically eliminated. Projection handles the output, but a modern interface is highly interactive. Users filter lists, network streams deliver updates, and automated tools suggest layouts. How do you safely mutate a centralized graph? You enforce a backward-facing write protocol called patch. No client, user, or tool can directly edit the document graph. Instead, they submit a proposed patch, forced through a strict typed validation gate. If the patch references a stale base address, the system rejects it entirely. Only a flawlessly validated proposal with a current address is allowed to merge. Patch is an absolute admission discipline. It protects the graph's authority by ensuring chaotic, asynchronous runtime environments cannot corrupt the interface truth. This discipline proves its worth when working with large language models. Treating raw AI output as a direct mutation layer is incredibly fragile. Models frequently hallucinate layout changes, suggesting component shifts without actually understanding the real-time constraints of the user's screen. Because the model is treated as just another editor, its output is packaged as a patch proposal. When an AI proposes an invalid layout change or targets an outdated address, the system simply refuses the patch. The document graph remains byte identical and perfectly safe. Look back at those 5 code panes from earlier. They are no longer isolated silos fighting for control. They are tethered projections, updating in instantaneous unison from a single verified node. You don't have to surrender your application to 5 conflicting systems. By enforcing the graph as the authority, cast as the projection, and patch as the admission gate, your interface stops drifting and adaptive truth becomes absolute.